It's my pleasure to be here today, and I have a lot to learn from everyone in this community, but I'll try to give you a brief summary of what we've been doing in the marine robotics field and how that is improving our knowledge of our planet in general, and also specifically in terms of climate. Okay, and I'm fumbling a little bit with my Zoom here, but I think I'll have it in a second. Slideshow. From the beginning. How about that? Okay, here we go. Okay, so I work in marine robotics. I've also done some work on terrestrial robots, but and we've been applying these to a variety of problems for exploring and understanding the ocean, including climate, but also in other areas, particularly understanding the geophysical processes that make the world work. And we'll be talking about some of these robots in a few minutes. Okay, I work at the Woods Hole Oceanographic Institution. We're the largest private research organization dedicated to the oceans. We do science and we do technology, and we do them together. And that's probably, I think, our most defining characteristic. We operate several large ships and any number of shoreside facilities. So what do we mean by deep sea robots? Well, they come in various shapes and sizes. That's one of the great strengths of the robotics paradigm, right? We can build lots of different devices that map to different tasks. When I first started back in the 70s, they were a curiosity, okay? But increasingly, they have become accepted. And now it's clear to say that they are mainstays of scientific exploration of both the seafloor and the midwater. And they can do many different kinds of surveys that we couldn't do before, and they can do them at less cost. The cooperation between engineers and oceanographers obviously is critical to all this. And by the way, as much progress as we've made, the ceiling is very high in terms of where we can take these technologies further. Marine robotics come in many shapes and sizes. You may be familiar with a few of these, but they all have their place, and many of these are specifically mapped to scientific needs. For example, things like the glider that you see over on the left. It's a very subtle device that is extremely productive for science. Okay, as an example of one problem that robots can really help with, how does our climate work and how is it changing? Well, we know that the ocean absorbs much of the excess heat and CO2 that leads to rising temperatures. We may be approaching a possible tipping point where the ocean circulation could flip. We know that that's happened in the past. And of course, sea level rise is something that we all have to deal with. And we need to understand better. So robots can contribute to this. Let me just say that whenever you talk about investigating the ocean, yes, robots have a strong role to play, but we have a lot of other technologies that have been developed over the last 150 years that are still very applicable. So, for example, if you're studying the Atlantic currents, moorings, okay, are still going to play an important role. You can put them out there. They can measure all kinds of important things, and they can do it for years. So existing technology and new technology is where we need to go. Here's another problem that where robots can really help, and I'll talk a little bit more about this in a few minutes. There's a phenomenon called diel-vertical migration, where animals travel up and down in the water column. Basically, they come near the surface at night, but they go down during the day, presumably, so they won't get eaten, okay? And this process, it happens all around the world, all the time. It's the largest migration on Earth, okay, for sure, without question. One of the aspects of that is it's probably a method for transferring carbon from near surface waters to deep ocean. And of course, this plays a large part in regulating our climate. So if we want to know how CO2 in the atmosphere then becomes CO2 in the ocean and then is possibly sequestered, meaning it's removed from the system, we have a lot of progress we need to make to really understand that, let alone the fact that we may want to enhance those processes if that's an idea that's on the table. Okay, one of the great tools that oceanography has produced in the last several decades is a system called Argo, okay? And if you have an idea that you want to build a robot in the ocean and that it should have long endurance and it should make important measurements, you need to know what Argo is and what it does. It's been around for decades, and they have these profiling floats that you see here on the right, okay? As robots go, they're not the smartest in the world, but they are extremely effective and they match very well to what scientists need to know. They descend to about 1,000 meters. They drift for a period, I think, of several weeks. Then they do a deep transect. Then they come back to the surface and they send their data back home. What is that data? Temperature, salinity, and increasingly other important geochemical parameters. We have thousands of them in the ocean. This is an international effort supported by many, many countries. And all of this data gets integrated and put it's accessible to any scientist in the world who needs it. It's probably one of the great scientific facilities that our community has ever created. There are over 5,000 refereed papers from 50 countries using this data. If you're interested in robots to save the planet, and you don't know about this project, you have something very important to learn. Here's how an Argo float works. Okay, so it descends, it drifts for 10 days, goes deep, comes back to the surface, sends its data home, and starts its next cycle. What does it measure? Temperature, salinity, etc. And of course, the satellite comms are greatly improved, super important data. And when you have 4,000 or 5,000 of them out there, they're easily deployed from any ship. They literally throw the float over the side in the cardboard box it was shipped in. You can't get much easier to deploy than that. And then they are not recovered, by the way. That's important. No. One little snippet of data from the combined Argo array is the average global temperature anomaly over a 20-year period. Okay. This is obviously important. I don't have time, and I'm not a physical oceanographer, but if there are any in the audience, this plot almost needs no explanation. This was the original goal of Argo, is to study climate changes in climate, and it has certainly succeeded in that. And like I say, 5,000 peer-reviewed papers. It's a dynamite system. Okay. Another reason why we need to explore the oceans, we need to understand how our planet works, okay? And many of you probably know the Earth has seams like a soccer ball, like a football, okay? And those are called the mid-ocean ridges. And those are the places where the new continents are being created through a process called seafloor spreading. I've spent a lot of time exploring that with our robots, and I think that we've really made some great progress, both in terms of the mid-ocean ridge and other interesting dynamic areas like volcanoes. And we'll talk a little bit about that. And of course, sometimes we have volcanoes on the mid-ocean ridge, or we have volcanoes not on the mid-ocean ridge. One of the great discoveries, not really with a robot, with a towed system. This was actually one of the systems we used on Titanic called Angus, sorry. It took 35 millimeter still pictures, and it could measure temperature. And it discovered a temperature anomaly. And when the pictures were processed, it turns out there were animals living there. And this was the first hydrothermal vent discovery. These are places where, through volcanic heat, seawater is convecting through. Long story, the chemists suspected this was happening. The geophysicists and geologists suspected this was happening. No one imagined it would also be one of the biological discoveries of the 20th century. A big shock. And from that first expedition, 32 published papers from that one expedition using Angus, followed up by Alvin, the human-occupied vehicle. Alvin did not make the initial discovery. That was done by this remotely operated system, and then they vectored the submersible to the spot. Showing how much progress we made in this over the years. This is an expedition that I was on about 10 years ago now, using our autonomous vehicle Sentry and our remotely operated vehicle Jason. And one of the themes of my talk is that these technologies all work together extremely well. So here we are, a couple hundred miles from Auckland, New Zealand, where we set sail on the research vessel Roger Revelle, which was operated by the Scripps Institute for Oceanography. This is the map that our autonomous vehicle made, Sentry. This is one of my favorite projects I ever worked on. I programmed all these track lines myself. I was a bit obsessive. There's a lot of constraints you need to satisfy when you're programming a robot for a task like this. You want it to follow the contours, but you want it to fly a straight line as it's following the terrain. You don't want to be flying up and downhill. You want to be flying along the contours, but you want to fly in a straight line. You want to be matched up to the previous track line. You want each grid to be matched up to the previous grid. You want to repair any holes in the previous grid, and you want to make sure you can link all these grids together. And I can obsess about this for hours. Simona knows this already. In any case, we assembled this beautiful map. Okay, yes, it's beautiful. It's also very important because it documented the this recent eruption, which is one of the largest eruptions that ever happened under the ocean. What did we do with that map? Near real time, okay, within a day or two of making the map, we use that map to plan the remotely operated vehicle dives. So the geologists were able to say, we need to go here, we need to take this sample, we need to pick up this rock. And if you know any remotely operated vehicle pilots, picking up the biggest rock is a very big deal for them, okay? The geologists might have different criteria for which rock they want, but the pilots want to pick up the biggest one. And you can see our pilots succeeded quite well here. So anyway, again, these technologies working together, helping to unravel this mystery. Okay, DSV Alvin, it's on its third iteration of technology. There is not a single original component from the 60s in this sub, but it's very effective. It's been working quite well. And hopefully I'm going to be able to get this YouTube link to work. Yes. Okay. And you're going to see some data that's just a few days old. Isn't it wonderful? They're still at sea. Okay. This is older data there, that eruption. Okay. That's in the history books, but you're going to see some data that's brand new. Okay, so this was the event on one day, April 28th, pretty recently. And we've explored this vent system many times with all of our technologies. The next day, April 29th, it's a whole different world because there has been a volcanic eruption on the seafloor. Okay, and you can find this. You can find online. You can find this. And there's a highlight coming up here that I think you're really going to enjoy. Check that out. That's active lava emerging from the seafloor on a mid-ocean ridge, never been seen by human eyes before. And this just happened less than a week ago. They're still out there, and we're watching the video and sharing it with our friends all over the world. I tell you, it's a great world that we live in. And now I have to figure out how to get out of this and get back to my presentation. How do I do that? I didn't practice this, unfortunately. Oops, I'm going to stop that. Okay, let me find out. I'm sorry, I'm fumbling here. I know. I get rid of this. Okay, we're back to my talk. Now, this whole theme of the AUV making the maps and then using that for a close-up inspection. Here's another example. This is actually on the Galapagos Rift. This is a map of the seafloor we made from the ship, from the vessel, from several thousand meters up. Here's a map that we made with Century. And our chief scientist has planned the Alvin dive in great detail using this map. Okay. When Alvin goes down on the seafloor nowadays, it rarely is off on a sort of wandering through the woods kind of thing. Okay. We've made maps with our autonomous robots and likewise for the ROV. And when that submersible goes in the water, it has a very detailed plan. Okay, go to this spot, take these pictures, pick up these samples. It's a whole new way of doing things. And we've been working on that paradigm since 1999. The first time we did that, we made a map with our AUV Abe, which is now, which was the first AUV that we built. I would make the map before the Alvin dive at like 4 in the morning. I would print it out on a piece of paper and I would hand it to the people who were getting in the submersible. And they loved it. Okay, now we have it all integrated. The pilot's display has the map on it. It's a great thing. Okay, other climate problems where robots can help. We can look at the physical oceanography in and around ice shelves. And this is our friends from the UK, National Oceanography Center, with their famous robot Bodie McBoatface, which can survey under the ice shelves. Okay, great story with the name. We'll save that story for another time. And this is Woods Hole Oceanographic's Nereid Under Ice. It's a tethered vehicle connected by a tiny little optical fiber. So you can teleoperate under the ice shelf or any other ice constrained environment, including deep hydrothermal vents have been explored with Nereid Under Ice NUI. And now they're working on a new variation on this, which is they can deploy a NUI-like vehicle called SAMS. It can autonomously fly under the ice shelf and then turn itself into a mooring that can telemeter data back over years. Okay, and the physical oceanographers really need to know what's going on under these ice shelves so they can understand the rate at which they are melting and how things are changing. This is just a great piece of work. It was just funded privately by the Keck Foundation. You can find more information on this website. Again, we talked about vertical migration. The animals, every night they come to the surface. Every day they go back down. While they're doing that, they are certainly transferring carbon. How much? And is that carbon sequestered? These are the things that we need to know. Of course, some of these midwater animals are incredibly beautiful and mysterious, and we just love studying them. I showed you this, this chart before. So again, the question is, does this biological activity accelerate the transfer of carbon to the deep sea? That's what we need to understand. We have tools we've used over the years. By no means, in oceanography, we're always drawing on the past and the rich heritage of the existing methodologies. Cameras, net tows, we still tow nets. They're still important. We use acoustics, okay, and we use all kinds of drifting instruments. This is a vehicle I've been working on for the past decade called Mesobot. It's specifically designed for midwater exploration. Here it is in some of its early days, and we used it to actually actively track zooplankton. That's actually what's over my shoulder here in my background. We use white lights, we use red lights. Why do we use red lights? Because animals can't, be careful generalizing about the ocean, okay? Almost anything you say will have something wrong with it. Most deep sea animals do not see in red. The ocean is as transparent as it can be to blue-green light. It's almost opaque to red, so the animals their eyes don't work in the red. That would be a waste. So if we use red, it's difficult because the attenuation is very high, but we can essentially not disturb the animals. And I'm going to show you a little recent example here, I think that you're all going to enjoy. This is Mesobot we're off American Samoa, so we're a very long way from home. And actually, I have to, my biologist friends tease me because these sharks are ubiquitous out there. It's a bit like squirrels in my backyard. And this is an optical lure, kind of a disco ball that we put on there. So we had red lights, which the animals can't see, and then we had the disco ball to attract them. Okay. And I have to say, if I was the director of a film and I was telling the shark what to do, this would be pretty much what I would ask it to do. So credit to the shark. And she decided she didn't really like that. So, okay, I'm going to go back to my slideshow from the current slide. Oops. Okay. And I fumbled Zoom once again. You know, maybe one day we're going to get good at Zoom. Almost, I don't know how long we've been Zooming. Okay. So we saw that one. We also use many different kinds of robots. Here's an example. We have our vessel, the exploration vessel Nautilus. We have the DRIX autonomous surface vehicle, and we have the Mesobot. And these three systems work together. They can communicate using RF on the surface, using acoustics when Mesobot is down below. DRIX can keep track of Mesobot. It can follow it. And it also provides a kind of acoustic overlook using down-looking sonars so we can see where the animals are, and then we can direct Mesobot into those layers. This is a very busy slide. I can talk to anybody later about how this actually works. But here you see the sonar record, and we actually are imaging these layers. You see this blue streak here, and we are directing Mesobot, which also shows up on the sonar, into the layer. We go into the layer, we take images of the animals, and then we do something else that's very special. We filter water, and we bring back what's on the filter, and that includes environmental DNA, okay? A genetic signature of the animals that live in that water, okay? And we bring those samples back they're preserved on the ship. They put in a minus 80 freezer. They're shipped on dry ice back to Woods Hole. They extract the DNA, they amplify it, and they send it out and have it sequenced. And they make these beautiful bar charts, and they give us a sort of global view of the animals that are living there. So the lesson here is we use a combination of robots to see interesting features, to direct another robot into that feature. We take images, of course, we measure all the physical variables, and we take physical samples of the DNA. Finally, we reach out to the public. This is a wonderful book. If you have young children or you have friends with young children, I highly recommend this book. Mesobot is a character in the book, and we are so proud of this. And it's about a lot more than oceanography. It's about being yourself and appreciating your differences. I couldn't believe how well this project turned out. Okay, with that, I'm going to close. I'm sure I'm over time. I apologize. And we can have whatever time we have for questions. So robots, lots of different kinds. They apply to lots of different scientific problems. Oceanographers and engineers working together, that's the key. And understanding the mysteries of our world. So with that, I think if we have any time left, we can have a question or two, Simona.
Yes, I think we might have time for at least one question. I can see one already in the chat, and Jessica is asking where we can find the book that you've been talking about.
Oh, okay. You can find it on Amazon. You can find it on the Woods Hole Oceanographic website. We have a gift shop, so I would direct you to the Woods Hole Oceanographic gift shop, and you can find it in the book section there. It's called, I think it's called Where the Weird Things Are. There you go. Where the Weird Things Are. You can find it on Amazon. You can find it in the Woods Hole bookshop. I love this book. Sorry to keep saying.
Yeah, it looks, I mean,
yeah.
Okay. So we have a couple of questions in the Q&A section that have been pointed out too. Thank you. So here is one. Do we know if most deep ocean animals cannot perceive difference in light intensity and we can use when we can use red light, or are they just unable to perceive the red color altogether?
Okay. As an engineer, I have been privileged to spend a lot of time with oceanographers who really understand these problems. Okay. The scientific literature in terms of the visual capability of deep sea animals is incredibly rich. Okay. Basically, if you catch an animal in a net and you bring it home frozen, okay, you can analyze the spectral response of its eye chemically. Okay. So we tow lots of nets, we get a lot of animals, we bring them home, and those the spectral response capability of those eyes can be studied in detail, and it's very well documented. I was shocked when I saw how extensive that literature is. So most deep sea animals, again, there's always exceptions, they have a very sharp peak in their sensitivity. It's 490 nanometers, which means blue-green, okay, which is where the ocean is most transparent. This is extremely well documented, and it's also documented behaviorally. Okay, some great pioneers in our field. So most deep sea animals and midwater animals are essentially blind to red. You know, animals near the surface. So, for example, if you're a fisherman and you like to go catch trout, okay, they live near the surface. They live in a very rich, colorful visual environment, and their eyes are sensitive to all colors. Okay, in fact, colors we can't even see. Okay, so I can just say that the visual capabilities of these deep sea animals is technically well understood. The behavioral aspects are still in large part a mystery, though, I should add.
More questions. So,
Okay.
yeah, does microplastic also affecting level of CO2 in the sea, as far as you know?
I can't really answer that question. I know that we're doing a lot of work on the microplastics issue. Unfortunately, most of what we're doing is figuring out how to observe it and understand its implications. I don't know that it has anything to do with the transfer of carbon, other than the fact that it's got carbon in it. But we do know there's been a lot of progress in terms of understanding the problem. The solution to the problem, in my personal opinion, has to be to stop throwing our trash in the ocean in the first place. Okay, this idea of somehow scooping it out of the ocean, in my view, is extremely problematic. Okay, we have to stop putting plastic in the ocean, period. And I can say that with a lot of confidence that that's the right answer.
Makes sense. Okay, one more question. Would you please recommend some references, sources, publication or research organizations that could quantify the carbon sequestration impact of biological activity in the upper ocean?
Ooh, that's a big one.
Yeah, take it on.
I can't quite put my finger on one um, let's say one primary reference that you could use. Let's see. I'll give you one clue. Go to Google Scholar and look at the publications from my colleague Kenneth Bissler, Buessler. He's a chemist. He spent his whole professional life studying what happens to carbon in the ocean. Okay. And so I will, if you go to the WHOI website, you can also find a website for his lab. And he's the world's authority on what's happening with the carbon, how you measure it, and another great scientist is David Siegel at I think he's at UC University of California, I think Santa Barbara, I'm not sure. Great scholars in the field, thinking big picture, thinking fine scale, the way good scientists do, and everything in between. So I could recommend David Siegel and Kenneth Bissler as good places to start.
Okay, I think I'm asking confirmation, but I think that we still have a few minutes. So
Oh, good.
I just
Oh, great.
wanted to ask you one more question that I see in the chat, and it's about which underexplored regions of the ocean is of greater interest for oceanographers, and could it
Ah,
be accessible
well,
using marine robotics?
that's like asking me which of my daughters is the prettiest. Okay. You know, I mean, there's no answer to that question. Um, let's see. Um, I would say I can't say what's the most interesting. Okay, the basic geophysical processes, and as you saw just last week, okay, the scientific discoveries that we make, the impact for that on understanding how our planet works is huge. Is that going to feed hungry people tomorrow? I don't know. Okay, I think it's very important, and it's important for us spiritually to understand this planet that we live on. So my heart will always be in that those problems and working with the geologists, the geophysicists, the chemists, and the biologists who study those mid-ocean ridge processes. In the last 10 years, I've been working on this midwater problem, and of course now I have great um, collaborations with the biologists and chemists who work in that field. I think that is absolutely fascinating. The midwater ocean is the largest biome on Earth. Okay, that's where all the fish live. That's where a tremendous variety of invertebrates, all these animals live. It plays a big role in our climate. I could spend the rest of my days studying the mid-ocean, the midwater ocean, and be very satisfied. The polar regions, obviously, that ice shelf problem, I think it's huge. It's important. And those observations that are made by robots and autonomous moorings under the ice shelf, coupled with all kinds of remote sensing observations that we can make, and we can really put that picture together and understand what's going on in these regions. And, you know, I live a few hundred meters from the ocean. Okay. There's big changes coming up, most likely in the next in the next century, and we need to stay ahead of that. So I can't tell you which one's most important or most interesting, but I feel privileged to have been able to work on all of them. So um, I'm very happy about that.
Thank you.
Yeah.
Okay, so I think if you we have one more question, but if you stay a bit longer and if you see more questions later, can you please answer in the chat? I think they're asking.
Sure. I'll be on. I have to say I'm heading off on vacation later today, so but I will stay tuned in as long as I can.
Okay.
And then I'm heading to the woods up in Maine for some digital detox. No
Sounds
phones,
amazing.
no cell phone,
Sounds
no
very
internet,
good.
no nothing. Just nature and good food and fellowship. So
Oh,
but
wow.
I'll stay on as long as I can.
Amazing. Okay, then the last question was, do we know if most deep ocean animals cannot perceive? Ah, no, sorry, we already asked this one. So the red line one. So we're all done. Actually, then
Okay,
that's mine. I
great.
wanted to know, how did you know like that the stroboscopic light was going to attract fish? Like what study is under
Oh,
that?
well, we completely ripped off one of our colleagues, Dr. Edie Witter, who's a pioneer in the field, and she built the first optical lure about over a decade ago, and she managed to attract a giant squid, which is one of the coolest things ever. Um, uh, you know, again, my biologists tease me about that shark video because, oh, great, you prove there's white tip sharks in the ocean. We never knew that. Um, uh, but you know, she made great discoveries with her optical lure, and so I work with other biologists in our department, a scientist named Joel Yopes, who studies fish for a living, and he advised us on how to design that lure and the colors and the patterns. So the way those lights blink. And I'm also proud to say that it was built by a high school student who was working with us for the summer. So he had a very successful stay with us.
Yeah, I remember that.
Yeah. All right. Yeah, sorry, you saw it when you visited
Yeah,
us.
I say.
Okay. So
Okay, well,
again, I'm going to
thanks
stay
so much.
online, and I'll try to stay connected as long as I can today. Thank you.
Thanks so much, Dana. It was wonderful. Thank you for having
Okay.
us.
Okay, great. Good luck with your meeting.
Thank you.
Yeah.